Hello and welcome. Thanks for joining us today. I know some of you just came back from the long Easter break. I hope you had a great time, connect with families and friends. And to many of us, family is home. And while we enjoy these moments connecting with our loved ones, let's not forget that many houses and homes are being impacted by the natural disasters, increasingly exacerbated due to climate change. As a technologist, these are moments where we hope that technology can evolve and help us scale our responses to support those disaster-affected communities. My name is Warren. I'm a senior solutions architect from AWS. In my past 5 years, I've had the privilege to work with such a business that made this possible, Nearmap. And today, I'm thrilled to have Dr. Michael Bewley, the Vice President of AI and Computer Vision Systems from Nearmap, on stage with me to share their story and our journey together to scale their AI capabilities using Amazon SageMaker. Let's welcome Michael.
Thanks, Warren. Well, humans, thank you to the few hundred of you who have made it in person, to those signing in your pajamas online. There are now more than 8 billion of us on this planet. In 2007, we crossed a threshold, with more than half the world's population living in urban areas. That's small urban settlements through to massive megacities with more than 10 million people in each. These urban areas are teeming with life and constantly changing. New suburbs are being built. Older ones are being gentrified and renewed. Towers rise and landscapes change, like here in Barangaroo just across the water. This is a 14-year history as captured by Nearmap of the development in that area. The rate of change is staggering. Dark masses of dark roofs and asphalt relentlessly appear alongside the more organically growing suburbs. These areas can form heat islands that are more than 10 degrees Fahrenheit hotter than their neighbours on those hottest of summer days. People are pushing into forest wilderness for the leafy environs. Despite the move towards cities, the number of people living in what's called the wildland-urban interface, where fire risk is higher, is increasing. You can see here some city-scale maps of tree coverage. Whole cities form on very different ecological backdrops, from the drier Perth on the left with lower tree cover, all the way through to Brisbane on the right with the highest and wettest environment. Disasters, born of events well beyond our control, devastate cities and towns, and humanity beavers away at the recovery effort. Nearmap is uniquely positioned to help us capture, quantify, and respond to the chaos. Now, satellites are capturing every inch of our globe in some way, shape or form, but they don't have high enough resolution to tell us about cities in enough detail. You can see here roughly the highest level of commercial grade satellite imagery you can buy on the left, and Nearmap's latest Hypercamera 3 imaging system on the right. This is capturing the same building. Drones themselves, they have a place, but for this purpose they are utterly useless. One drone can capture a city block before it runs out of batteries. Now, imagine the kind of program you would need to capture more than 100 million buildings on at least a once-a-year basis. It's mind-boggling. What that leaves is aerial imagery, pictures from planes. It's a very fragmented market overall, actually. Nearmap is in the top handful of global companies with 4 countries under our belt. In Australia, we're capturing more than 95% of the population 1 to 6 times a year. In the last year, I think we captured about 1.5 million square kilometers of imagery. And there's no one from an aerial perspective who has an AI system running reliably and repeatably on every flight to produce automated maps, except us. Earth observation is a term that has really become entangled with a name for satellite companies, but it's interesting that it seems to have turned focus to be more around space. It's hard to put things into space. really hard. You've got to launch them, keep them alive, and bring them down again safely. But for Earth observation to truly meet its goals, you need routine, reliable capture of imagery, turning that into real data as signals over time, not just having pictures. We have a growing data set with more than 60 petabytes worth of Earth observation imagery and growing rapidly. After a decade of designing intricate camera systems, of building automated visual products, we released our beta in the AI space in 2019. This video I'm about to show is all based on real data. I can't believe that was 5 years ago that we made that. In the last 7 years, we've been through a cycle of exploration, core development, and productionization of AI on top of our imagery and camera systems. I'll tell you a little bit of the journey now. It started in 2017. I joined as the first principal data scientist in the company, and it was really living the dream. On the one day coding and developing some prototypes, the next day talking to the CEO about potential strategies and future products. It became clear pretty quickly that we had 4 secret ingredients that meant we should go really hard in AI. One was software. I strongly believe that unless you have a solid software foundation, that's development practices, operation in the cloud, everything's scalable and working seamlessly, you cannot begin to build a successful machine learning product. So that's table stakes, and we had that. Secondly, hardware. Nearmap's also a hardware company. We design and build those camera systems just over the water in the city. Hardware is really difficult. It's in many ways more difficult than software. You make one mistake and you're set back by a couple of years because you went down a wrong turn. Seeing the company having developed multiple generations of camera systems, that gave me the confidence that we had the organizational tenacity to start building a machine learning product, not get bored halfway and actually see it through to the end. And that has panned out. Third is data. It's no secret in the machine learning game. If you want to do well, you want to succeed on the back of a special, unique data set that is unparalleled, because then you can build things that are unparalleled. And we have that in spades. Fourth, and not least, is customers themselves. We had a large customer base looking at our imagery instead of driving on site, and they were already asking us questions. Can you automate this? Can we see things recognized automatically? Can we have more automated workflows? And we saw VC money pouring into startups doing machine learning on imagery. There was clearly something to be had here. The CEO leaned in and effectively rebranded the company from aerial imagery to location intelligence, really even back in those early days. It was a pretty big shift and an early call. Our CTO leaned in, we tripled the size of the AI team, and we pushed the big red button. That big red button, with a team of maybe 5 people, we built a system that could take a deep learning model, run it on aerial imagery using Spot GPUs, and then produce a data set. So, over a 3-week period, we think we pulled all the K80 GPUs that were available on Spot in the US over that 3-week time. We had 3 Kubernetes clusters going with something like 5,000 or 6,000 GPUs rolling. We spent something like $1 million and produced more than 1 million square kilometers of data. That was the beta, and the video showed just a little glimpse of what came out of that. From there, we entered our first generally available product, where customers could actually explore and see maps for themselves and download data. We then discovered the enterprise play. We had some really large customers who were excited about our data, but they wanted fast APIs and to be able to get data with high throughput. I think in the first year, we had more than 1 billion API requests on our AI API. Various product iteration cycles, we've released 5 production generations of AI system at this point to add new attributes, add a whole range of new features that I'll talk about. And then really at the end, look, we think we're leading the market in this, but if you pause even for a moment in the AI space, the pace of research, of hardware development and other things going on means that you can't afford to slow down. So you have to redisrupt. We think about AI in 3 different ways, which I think is quite helpful. Our CTO broke this out for us. There's adopting, so here's taking AI tools off the shelf where you just basically use them as is. That's table stakes. There's all sorts of Gen AI and other things where your company might not be doing anything special, but you've got to get into the tools and use them. Then you have build. This is where you have some kind of data set or use case where you've got to train some models and build a little bit of software. That's where you need some more tools, but the third bucket is where we went. It's the invent category, where you've got something so truly unique and special and you believe in the opportunity to the extent that you're willing to sink into a journey like this and build something that truly no one else has. It's a path that's not for the faint of heart. You really need to know why you're doing it and to approach it with high conviction if you want a chance to succeed. One of our invent steps was to build a custom deep learning model where one model runs in all 4 of our countries, unchanged. It's the same software stack and machine learning model. And it produces over 100 layers. These are a couple in the high definition vector map that we produce. So far, we've run something like 10 million square kilometers of imagery through that system with pixels the size of playing cards. Turning that into numbers, that is 10 quadrillion RGB values, which have been turned into 10 to the 16 probabilities. It's a lot. So what do those numbers do to make all that worthwhile, all that compute and data and storage? Let's walk now through a number of customer verticals and use cases, and I'll show you a little bit of what's possible and what is actually getting done out there today in the real world. Insurance is a big one. Insurance customers were some of our first keystone customers in the AI space, kind of doing large data pools. They're doing underwriting and claims. They're doing fraud detection, reasoning about future risk, past events. They're trying to actually pay out claims quicker than the customer realizes the extent of the damage to their property by responding rapidly. That's a good thing. And they're seeing climate change and thinking about portfolio level risk, understanding what it means for their entire book of business and the future of risk. These guys, their job is to make money off understanding risk, and they're taking this space very, very seriously. There's also local government, which is huge. We cover historical studies of vegetation, future planning, development, pool compliance, emergency service management, community resilience, and there's an eclectic long tail of companies using us for anything from corporate strategy to solar installation, rescuing koalas to keeping our beaches safe. We also have some of the biggest enterprise and government organizations in Australia on our books as customers. The use cases are so rich and diverse that I can't even begin to scratch the surface today. So I want to start this customer-focused section on shifting from mapping to monitoring. Mapping is something you're all well familiar with. Your phone or your device, you're looking at where you go. You want an up-to-date, accurate map of how the world stands today. Monitoring is where we say that actually, history is important because you need to reason about history and understand the changes that have happened if you want to reason about the future and what will happen. If you want to look at a vegetation study over a decade, as we have a whole bunch of local government customers doing, they buy our tree data this year, 5 years ago, 10 years ago, and they look at where the trees have gone. We have a large local government organization in the US with maybe 1 million properties in their zone. they're building a simulation of how and where their population will live over the next 20 years. And that's been seeded with Nearmap building footprints and other attributes. The Nature Conservancy is using data to monitor wetland changes in their sanctuary areas in Australia. There's so many things going on in this monitoring space. Some of the tools at our disposal, probably the largest cause of urban change is construction. And you can get a great picture of construction just from a single date. You can get individual buildings, all the way through to zooming out the area around Badgerys Creek, looking at the airport as a whole, the roads nearby, and if you zoomed in, you get these little pink dots the size of playing cards picking up a little bit of construction repairing the edge of a roof. The detail and the scale is just mind-boggling. If what matters to you is an up-to-date picture of how the urban world is changing and where this construction is happening, you can get it on tap. But we can go further than that. With the capture program and vision systems and AI running like clockwork, we can zoom out to the suburb level. This is Marsden Park with trees and buildings. Slightly different makeup of suburb, this is Wahroonga, again with trees and buildings. Now if you summarize information at a suburb level, you can look at it on multiple dates. I did that a year or two ago in Adelaide and saw that over the course of a decade there was a 9.8% relative tree cover loss. One of the suburbs that lost the most tree cover is called Vale Park. It's a mature suburb. You'll see orange buildings, pink construction sites, green trees, yellow solar panels. This is one shot every year rolling through the decade. Urban infill is where a big block becomes a block with a few buildings on it. And you increase the density, and you'll see that graph where tree cover drops. Shortly you'll see this is the tree cover at the start of the decade, and that's the tree cover a decade later. The difference is clear, it's stark, and it's quantitative. The wiggles you see are actually really nice seasonal variation that can be factored out, so you look at the summertime peaks in the graph. On the other side, you can see growth. One of the suburbs with the highest growth in Adelaide was Northgate, a young suburb at the time we started capture, little green dots where saplings had been planted, and they're watered, and they're cared for, and they're grown. There's so much out there about how many trees we plant, but who's checking that they actually make it to maturity where we get actually all the benefits of tree covers. A sapling doesn't do anything, it's the big mature tree that matters. And that before and after view of the decade is just, it's quite staggering. It's a wonderful picture of what can happen with a new suburb if those trees are nurtured correctly. We can turn to search. This was on a data set that I just built up on our AI data with about 5,000 or so suburbs in Australia in it, and I asked it, which suburbs had the largest amount of building cover change in the course of 4 years? Narimba in Queensland has almost double the change of the second place. So let's have a look at more detail, that'll be interesting. These before and after, not over a 4-year span, but over a 1.5 year span. You can see in that graph the building cover goes from nothing to almost 40% like that. It's very fast. The tree cover was pretty low to start with. It was, I think, disused farmland. It drops to 0, then it starts to creep up to maybe 0.5%. Now 20% is where we want to get to, generally, or higher. Will it follow the path of Northgate? Who knows? Let's track it over time. Solar, interestingly, looks very different in these new suburbs. While people in more established suburbs agonize about whether to do solar on the roof, whether it's going to change the feel of their property or whether they get around to it, these guys just tick a box, and they very quickly get to 25 square meters of solar panels per building on average in the suburb and maintain it. It's actually a wonderful facet of these new builds. Then we can go broader. We can stick all 5,000 or so suburbs on a single graph, right? So this is, each dot is a suburb. The size of the dot is the population in that suburb according to the latest census. The color is the capital city. The vertical is your tree cover, the horizontal is your building cover. Where in Sydney, if you look at that red top edge for any given building cover, in the top left of the graph, you see really high tree cover in the kind of leafy North Shore of Sydney compared to other cities. All the way through in the bottom right, you still have the highest relative tree cover in dense building areas. These are places like Annandale with lots of buildings, but still quite a few trees. Brisbane actually has higher average tree cover. It sits in the middle there. Sydney kind of varies around more, whereas Brisbane's a bit more consistent. And then you see a really interesting effect in the bottom left. you see these large green blobs, really popular suburbs in Melbourne that have high populations. They're pretty new suburbs often. The building density is not that high and the tree cover is really, really low. What's going to happen with these in future? This was 2019, and that's 4 years later. I'm going to go backwards and forwards a couple of times just so you can see the shift. It's subtle, but what you'll see is these dots dragging slightly down and slightly to the right. That's slightly lower tree cover and slightly higher building density. I find it astounding that this kind of effect can come as the macro addition of all the little effects from each of these 5,000 suburbs. Each suburb is made of a whole bunch of properties, and those properties are made up of pixels the size of playing cards where we've run a deep learning model. All we've done is use that data and spliced in a bit of the latest census data. For reference, Nearmap shot from the bottom left to the bottom right of this graph in a year and a half. So this is our nation on a page. What's it going to look like in 4 years' time? Or 40? Finally, we have the tools to monitor properly, rapidly observe the impact of policy, of development and other changes, reason about what we want our cities to look like, and perhaps plan for a better future. We can stretch back further. Because we run the same software stack and model in 4 countries, you can compare countries. So we see blue dots is suburbs in Australia, red dots is suburbs in the US. The typical tree cover in a city block is about the same. Difference in the tails, but the median's about the same. Australian city blocks are much more densely built than ones in the US. And this is fairly common knowledge that things are more spread out on larger plots there. But again, it's fascinating that this builds up from just those little pixels, and you come up with findings like this. With dozens and dozens and dozens of attributes, there is so much to explore. It's amazing to think about what we might learn from this data in future. We're just scratching the surface. The second main use case as we move on from monitoring is tech-driven disaster response. This is a picture of Lismore, recently in New South Wales after a flood. We respond to natural disasters as fast as we can by getting a plane in the air. We get out on site, sometimes within hours, sometimes within days, to capture imagery as fast as humanly possible, process it, and put it online, sometimes in hours, sometimes in a few days. Now, traditionally what happens in this space is drone, aerial, or satellite imagery is captured and published, and an army of volunteers will jump in and start labeling buildings to find out where the damage is and how we can direct response efforts. It's a heroic effort, but as of recently, this practice can be relegated to the history books. We recently released a super fast AI product for building damage detection, this was late last year, that went live just before Hurricane Idalia hit in the US. This is a map of the automated building damage detection in one of the towns. Over the course of a few days, we did, I think it was 37 flights to capture imagery. The AI was produced fully automatically while the team slept in their beds in Australia. Within 3 hours of each survey of imagery being published live, the AI was available behind an API. The impact that this can have for first responders, for insurance, for communities is huge. It works in hurricanes in the US, in wildfires in Australia. But when it comes to disaster, while it's great to identify damage once it's happened, what you really want to do is predict and prevent it in future. This is a rundown warehouse in Weed, California. You can see from our AI layers, red structural damage, yellow rust, blue ponding, pink junk and wreckage. We're actually now running machine learning models on top of our automated maps. This particular one summarizes the state of the roof overall. It's a very poor roof, which is indicative of a whole range of risk factors. Actually, within a few months of this image being captured, according to media reports, a fire started in or around this warehouse and the warehouse burnt down. The fire then spread north and devastated the township just north of it as it was driven by the wind, and then went further north into the Californian forest in a dry summer. As you zoom in on a patch of that forest, you can see exactly how dry it is. There's trees, but if you look in the background, you can see some downed limbs, you can see trees without leaves on them. You can see it more easily if we put our AI layers over the top. Detecting trees is easy. Pink here is finding trees with no leaves on them. Red is finding bits of vegetation debris lying around on the floor. You can see a hole in the top middle where there's less of that sort of stuff, and that is the area that survives the fire the best. So we're not just looking at where the vegetation is, but what's the fuel load like? What's the health of the vegetation in that area, and what might that mean for fire risk? Now, we're going to combine some things. We're going to combine monitoring and that sort of search from earlier with disaster response. I looked in our Australian data set for the date and the location where there was the highest number of tarpaulins per roof that we'd ever captured. It turned out to be the Berowra Christmas 2018 hailstorm. I actually have friends from Berowra and I had dinner with them last week. They said this hailstorm was a double whammy, it hit twice in the same day, and it is burned into the memory of every resident there because it was such a big impact. Here we're going from damage detection to predicting future risk to actually monitoring the recovery of an area over time. So straight after the event, around 1 in 3 roofs, actually a little bit more, had a tarp. That is a very, very large number of roofs that need repair. 3 months later, our capture shows there's been a substantial amount of repair, but there was a huge bottleneck. There simply weren't enough people to repair the roofs quickly, so they were playing catch up. 12 months from the disaster, that effect is no longer present, but there's still some buildings that have tarps on them. Why? Are there insurance issues? Are there problems with the building? Are there vulnerable populations? We can use this kind of data. I'm really excited about the possibility of this helping resilience of communities, targeting relief and assistance and support where it's needed most, and checking that that support has been given and that we've recovered. I am so overwhelmed by the power of one deep learning model to drive everything I've just talked about and have meaningful impact on the world we live in. We're just scratching the surface. Now, we're at an AWS Summit, and I think I owe you some more technical explanation of how all this works. So this is our very coarse architecture with a labeling system, a model training system, a prediction engine which runs inference. We're going to focus today on the model training system. This is the system that produces that special deep learning model that then gets used in a whole lot of different ways. So the deep learning revolution started with something called the ImageNet competition, for those of you who know it, where people were trying to predict one of 1,000 different categories for an image. This was things like which breed of dog or cat it was. Inspired by that approach, I was discussing with the team and we worked out that if we can build these vector maps where all the layers come from a single model, the benefits for cost of run are huge because you're sharing features between all these layers. Your incremental cost is not linear as you add new layers. The statistical performance will improve as well, again because all these layers are sharing semantic features where they can share information. So the mantra for the team became build for 1,000 layers. We had some talented deep learning folk that cracked a way to do this for semantic segmentation, which is not easy. You face memory limits and it's quite tricky, but we figured it out. And then the production teams built systems that notionally can scale to 1,000 layers. Now we started with about a dozen in earlier things I've shown you. Then we had 27 layers. Then in Gen 4 we had 49 layers. Gen 5 had 78 layers. And we're pretty close to releasing Gen 6, which I can't tell you exactly how many layers it'll have. It'll be somewhere between 100 and double the number of layers that we have today, still in one model. So we can train these models, but at what cost? It's not actually the financial cost of training these models that's the problem. With a data set of over 1 million labeled images, we had a rack of GPUs in a data center, and we were training on 4 V100s at a time. Now those 4 GPUs would burn for 6 to 8 weeks to run to converge on a single model train. Now, this is a pretty big bottleneck. Those of you who are in tech in any way know that your speed of iteration is critical, whether you're doing software development or machine learning. Your cost of experimentation is directly related to your speed of innovation. So we knew we had a problem, so we embarked on a full rewrite and rethink of how we do training. We shifted from TensorFlow to PyTorch Lightning and rewrote our whole training harness and all of our data loaders. We shifted from owned GPUs in a data center to working on the cloud using SageMaker training. And we had tight collaboration with the AWS team the whole time. So what happened to that bottleneck? How did that work? It was close partnership with AWS and a lot of innovative tech that we built. I'm going to invite Warren back on stage to talk about how things looked from an AWS perspective throughout this collaboration. Thanks, Warren.
Thanks, Mike. What an inspiring story. And all those unique challenges Nearmap faced, how good was that? But it's true, scaling brings us these common problems. Slows down our speed of innovation, resource allocations, and also security and operations overhead. But the world of AI brings a whole new dimension to these challenges. Start with the innovation speed. The complexity of AI model development and unpredictable nature adds frictions and naturally slows down our ability to innovate. Data scientists, on average, iterate and refine a model 8 to 10 times before deployment. That's way more time consuming and exhaustive compared to traditional application development. But when we look at the time they spend, according to industry research, over 30 to 50% of the time actually spent on wrestling trivial tasks that's not related to core ML development. Configuring the environment, pulling down the right container images, installing the drivers, whatever that may be, it's a 50% of the time productivity impacted. I still remember the days when we started working on this challenge with Nearmap. We spent days just configuring these NUMA settings on the EC2 instances to benchmark the right memory performance. In a field where speed is a key, this is a serious handicap. Next, resource allocation. Now, as Mike pointed out, predicting AI needs and all the resources required to satisfy the growing data and team is a tough job. But it goes beyond just computational resources. AI is a highly specialized domain and concentrated in a small group of experts. Now, these experts tend to do everything themselves, like when Mike started, when they're small. But it's not efficient use of their time when they grow to a certain size. With expected growth of 40% in the AI workforce, the real challenge in front of us is how do we empower and enable the rest of the organization in providing the environment and right tools so they are able to experiment, try out, and ultimately contribute to projects and ideas. This will allow us to more evenly distribute our resources, budgets across the whole organization. Last, scaling leads to fragmentation and often drifts security protocols. And it makes systems harder to manage and more vulnerable over time. We know this. But what we don't realize is AI accelerates this. 85% of attacks, security attacks, are AI related, more specifically generative AI. This sends us a clear message. Having a right security strategy from the outset is critical to ensure the long-term success, minimize risks, and also reduce operational overhead before we get to the petabyte level. So balancing between this depth of iteration, which impacts of the speed of innovation, and the breadth of your resource distributions to unlock and empower more potentials, while keeping security and operations in control, are the core challenges to scale AI. And the answer, as we discover through our collaboration, lies within leveraging the right tools and platform that is specifically designed to address these issues head on. Now this is where Amazon SageMaker steps in, transforming the way Nearmap experiment, develop, and build their models. SageMaker isn't just about providing the computational resources. It actually offers a suite of features that accelerates the entire AI lifecycle, from data wrangling all the way to deployment management. Now, in the context of training and development, there are two key components Nearmap adopted. First, SageMaker Studio. It's a fully integrated developing environment that offers a unified interface for developers and engineers to prepare, build, and evaluate models. It also offers an interactive notebook collaboration to facilitate seamless teamwork. SageMaker Training Job, a fully managed service for automated training and tunings. It takes care of the whole life cycle of a training from data loading all the way to model artifact generations. With these two combined and their seamless integration into other AWS services like IAM, RDS, or S3, it allows Nearmap to streamline their entire workflow for their model development trainings seamlessly. And this helps them to speed their innovation, more effective scaling, while keeping security and operations in control. Sounds magical. Let's delve into it. First, speed of innovation. So how did exactly SageMaker help them? With a flexible infrastructure and effective scaling handled by SageMaker, the data scientist is able to run 8 to 10 concurrent experimentation. Each carry different hypotheses and model configurations. This basically eliminates all the bottlenecks Mike was talking about associated with a sequential iteration and finite resources on the previous environment. With this, they're able to, with the fan-out strategy, the team is able to release the model at an unprecedented speed. It's not just about single model development. It's also about providing an environment for the data scientists to independently build and train models. SageMaker Studio and Domains offers the environment to allow them to do that without worrying about the instance types or sizes or the capacity availability. It's one click away to switch from CPU-based training to GPU-based training without the environment being impacted. At peak, Nearmap used up to 30 different instance types just in development alone. It really shows the scale and the diversity of their innovation. What this ultimately translates to is they can release multiple models into the production environment either simultaneously or independently. With all the heavy lifting, now Nearmap's data scientist team is able to focus on what they do at the best, building better models, stay on top of research, or improving the performance and accuracy of the existing model. With our close collaborations, from the initial enablement all the way to bi-weekly hack-a-day session, the team is able to migrate their single node, multi-GPU training for the model into fully distributed training using data parallelization natively supported in SageMaker. And this has helped them to reduce the overall training time from 3 months down to, I'll leave that secret for Michael to review at the end. Innovation isn't just about tech, it's about the impact. With all the efficiency gains, it means Nearmap is able to release better AI layers and insights into the market at unprecedented speed. It unlocks a whole new wave of innovation and use cases too. Change detections, Michael pointed out, all the way to better building outlines. This is where the real value lies. Next, scaling the team. I want to focus on the human aspect of scaling, given SageMaker is taking care of all the computational parts. Often bottlenecks associated with the scale of hypergrowth team is the ramp-up time. It could take days and weeks for the environment to be ready for the developer or data scientist to become productive. Through integration with the existing single sign-on flow and the SageMaker domain profile, they're able to centralize the configuration of their environment, templated with all the pre-installed libraries and packages. And the developers can launch straight into it and ready to become productive immediately. This has helped them to eliminate and reduce the ramp-up time from days down to hours. To further improve their productivity, we've worked with the Nearmap team to cater for different preferences to integrate on an innovative solution to integrate with a local development environment, like Visual Studio Code or PyCharms. This has helped them to minimize the productivity impact when they migrated from the on-prem environment into the cloud. It has also standardized their development experience, both in the browser as well as locally. Now that's the starting point. As you iterate through the model development, you want to make sure that you're unblocked. And SageMaker provides that self-servicing capabilities so that data science team can own their own resources. They don't need to be dependent on the IT and operations team anymore, or minimize the impact, let's say. This is the only way I see to break that golden ratio between ML team and the DevOps team. Of course, With the great ownership comes the great responsibility too, and the cost is a part of it. With the fine-grained control of all the resources and the tagging policies associated with it, the individual member is able to gain full transparency into the developing environment, as well as the training jobs spin off from it. Now this is less about monitoring and reporting. It's about gaining insights and continuously improve the efficiency of their model development. What this ultimately translates to is better profit for the AI products and services. With a seamless onboarding process and all the autonomy and flexibility, Nearmap sends a clear message and showcases to the community that they can provide an environment for the team members to make meaningful impact to the organization, to the customer, and ultimately to the community. It attracts talent who share the same value and vision as the business. Last but not the least, SageMaker has helped the Nearmap team to massively improve their security postures. No more data and models move in and out of their AWS environment and duplicate the security efforts and increase the attack surface. With bringing everything into SageMaker, they're able to enforce all the security policies and the governance that defined at the top organization level and delegate that down to the individual AI projects, resources, and developing environment. With the fine-grained access control built into their single sign-on flow, they gain full visibility into all the developing environment, as well as the training jobs being from that. With the built-in auditing and logging services that's supported by SageMaker, they're able to gain full transparency to all the activities and facilitate real-time monitoring and really simplify their auditing, their governance and compliance processes. So this is the high level, what we've worked in the Nearmap team to overcome those challenges they face when they scale their AI capabilities. I'm going to now pass back on to Michael to talk about the impact for the business, and more importantly, what's holding future for Nearmap.
Thanks again, Warren. So we talked about speed before. If you can take 6 to 8 weeks to train one model, the actual iteration time of releasing a new model in production is 3 months. Too slow. Where did we get to? Well, a couple of weeks ago, we trained one model on about 80 A100s, that's 10 different nodes, and it took about 26 hours to run instead of 6 to 8 weeks. That is on a data set that is more than double the size, on a model architecture that is more than double the size, and with something like double the number of layers of last time. It is a remarkable difference. It actually means that the release cycle, if I say we need the next model, it actually takes about 2 weeks because the human effort dominates rather than waiting for GPUs to converge. This brings in the world of elasticity. It used to be kind of convenient to have steady state GPUs that we owned because you've got a couple of data scientists training long-running models, you plan it out, you've got near 100% utilization of those GPUs, nice and cost efficient, works well. When you can splash to 10 P4Ds at once, you kind of want to give them back when you're done because you don't want to keep paying for them. And you also want to choose the time of your experiment. So we've gone from a very smooth profile to a very spiky cost profile. You have to be on the cloud for that. It simply doesn't work to own 10 times as many boxes as you need on a normal basis. Sharing then becomes a really big thing. So again, it used to be easy in that steady state world with a couple of people planning experiments, but when you've got a growing team, people are starting to do spiky workloads, you've got all these complicated negotiations around who's using which machine and for how long, and you've got different R&D projects where you're making really boring negotiations around which box gets used by who and impacting project timelines. Now, as well as training models rapidly, we can train them independently, so these different project timelines don't need to interact with each other. The data scientist just gets in and trains a model without needing to talk to their colleague about it. We use SageMaker Studio for our ad hoc development. We basically have a standardized development Docker container that pops up. We use SSH and VS Code a lot for jumping into a SageMaker Studio instance. This is from our ops teams all the way through to our R&D teams. Then when it comes time for a more serious training run, we use SageMaker Training. Now, This section wouldn't be complete without a bit of discussion around partnership. When you're using really dense, expensive compute like this, when there are global GPU shortages, when you have rapidly evolving needs, and you're trying to run as hard and fast as you can without tripping over your own feet, you need a little bit more support than the public docs will give you by just reading them. So early on in our journey with the SageMaker team, they flew out an expert to hang out with us for a week and get us started on the right path. They have helped us with all sorts of tips and advice on where they're headed. They've fixed bugs for us, worked on feature development for us, and really, as we've pushed their boundaries, they've helped us to push ours. I think a really notable feature of the way they work has been that rather than their strategy seeming to be, let's figure out how to get these guys to spend more money, the strategy seems to be, let's figure out how to get these guys to win. And so they've genuinely been helping us succeed, and that's been a really successful path on both our fronts, frankly, over the last few years. So what's next? Well, there's that 60 petabyte data set, and it's just sitting there. And now we've got the tooling and infrastructure to throw as many GPUs as we want at it. And the research community has worked out ways to leverage large collections of imagery. I know all the talk is about text at the moment, but large collections of imagery in an unsupervised manner that don't require human expert labels. We've got a competitive advantage just sitting there waiting to be unlocked. All it needs is the budget, the researchers with ideas, and we can go somewhere that simply was not possible before. And what else? Well, that new camera system I mentioned, it captures higher resolution, higher quality imagery that can detect more things. The multi-angle source imagery is higher resolution and better, which produces better quality 3D. There's an infrared channel. The number of opportunities for ML research that leads to direct products that impact customers is enormous. We've set a really ambitious target with what we do with SageMaker training over the next few years, and I can't wait to see what our team does with it. Warren, I'll hand over to you to close.
Yeah, sorry. I know we're a little bit over time, apologies. Just before you go, if you want to learn more about SageMaker or AWS in general, we've got the free 7-day trial of AWS Skill Builder. And last, not but the least, I appreciate if you can fill in the survey for us so we can improve our content and future presentations. Thank you.